Hi.
Hey everyone, welcome back to Etale Cohomology. So today we're going to talk about one of my literally favorite topics in all of math, which is Brauer groups. But before that, are there any questions about what we've been talking about so far? All right, well, if not, let me remind you where we are. So here's a reminder. So our current goal is to prove the following. So C is a smooth curve over an algebraically closed field. And we're trying to compute the Etale cohomology of C with coefficients in GM. And we've already computed it in degree 0, in which case it's just OC cross of C. So that's in degree 0. And we've computed in degree 1, in which case it was pic C. So that followed from what we called Hilbert's theorem 90, which was a special case of faithfully flat descent. And then the goal is to show that it vanishes in degree bigger than 1. So we've done this, and so far degree 0 is, degree bigger, this should be bigger than 1, not bigger than 0. So far, all higher degrees are a total mystery. And so today, what we're trying to understand is the number after 1, which is we're trying to understand I equals 2. And in fact, we've reduced this to some question purely about Galois cohomology. So we've reduced this to understanding. So this is what we did it last time. HI of the function field of C with GM coefficients. And also HI of the strictly Henselian local rings at closed points of C. So this is the strict Henselization. And let me just remind you, that was the stalk of the structure sheaf of C of OCX. All right. Are there any questions about this? So today we're going to try to understand basically the Galois cohomology of a field with coefficients in k bar star, part k bar cross, or GM if you'd like it to think about it as a sheaf on the Etale site. We're really basically going to be discussing I equals 2, but it will turn out, and this is kind of a general principle in group cohomology, that if you can understand I equals 1 and I equals 2, so then you can understand cohomology in all degrees. That's not always true, but it's often true in group cohomology, and Galois cohomology is a special case of group cohomology. So are there any questions about this? So I claim this is stuff we've already done, modulo this question mark here, and modulo understanding what these groups actually are. But does anyone want me to remind them a little bit about why this is what we're interested in? All right, good. So you guys are all on top of things. So maybe just a reminder or just a comment, like in general, H1 is not that hard to understand. Like that's something, classes in H1 have a geometric meaning, and we talked about that geometric meaning. They classify torsors. And often you can think of torsors as real, like physical objects, or at least insofar as any scheme or sheaf is a physical object. So H2 is much harder. There is some abstract sense in which it classifies a real object. So elements of H2 correspond to certain stacks called gerbs. I'm not going to talk about that. But the real miracle is that H2 of GM has real meaning. So it's very closely related to the Brauer group. And elements of the Brauer group, as we'll see today, are at least closely related to real physical objects, so certain torsors. Okay, so let me remind you. So we defined, if X is a scheme, we defined the cohomological Brauer group of X. And some people just call this Brauer prime, so Brauer prime of X. This was defined to be, you take the Etale cohomology of X with coefficients in GM, and then you take the torsion there. Okay, and at the end of last time, we started defining the Brauer group. So we said we can look at the image over the union over all n of the set of PGLN torsors over X. So let's say Etale locally trivial. Trivial PGLN torsors over X. And I claimed that there was a map to H2 X Etale GM. And we started working out that map last time, but we didn't quite finish giving an explicit description of it. But we made the following definition: the Brauer group of X, and right now all we know is that it's a set, is the image of this map. So the Brauer group, which we don't know is a group yet even, is going to be defined as the image of this map, which is, at least I hope you agree with me, the source of this map, the set of PGLN torsors, is a reasonably explicit geometric object. Okay, are there any questions about this? Okay, so can anyone remind me how we define this map from Etale locally trivial PGLN torsors over X to the Etale cohomology of GM in degree 2?
We use the GM to GLN to PGLN.
Yeah, so this map delta here, or I'll call it delta, and the reason why is that as Arvin suggests, let me move delta a little bit over. As Arvin suggests, this is coming from some kind of long exact sequence in cohomology, and the weird thing is that it's coming from a long exact sequence, a short exact sequence of sheaves, where not all the sheaves showing up are abelian. So okay, so what is the definition of delta? So it's the boundary map, and I'll say what this means a little bit more explicitly, from H1 X Etale PGLN, or really the union over all n, this thing, to H2 of X Etale GM, arising from the long exact sequence, arising from the so-called long exact sequence. I'll say what I mean by it, associated to the short exact sequence of sheaves, 1 to GM to GLN to PGLN to 1. So this is a short exact sequence of sheaves of groups on X Etale. Okay, and we even, at the very end of last time, we even argued, so exactness, left exactness is not so hard to see, and at the end of last time, we argued that this was actually even exact in the Zariski topology, and that was because this map GLN to PGLN is a GM torsor, and so it's Zariski locally trivial. Okay. Are there any questions about this? And then we had a lot of discussion about what the sheaf PGLN actually looks like explicitly. Okay, so let's talk about what this boundary map means. So hopefully this is all this is familiar to you when you've seen in the case of a short exact sequence of abelian sheaves, and I don't at all expect this is familiar in the case of non-abelian sheaves of groups. So let me maybe make a remark. So as far as I know, the best reference for this, and maybe someone else can suggest another reference, is Verdier's book, or sorry, Giraud's book. Giraud's book, Cohomology non-abelienne. So this is something that I would say you can find in a bunch of places, this sort of long exact sequence, or sort of partial long exact sequence associated to a short exact sequence of possibly non-abelian sheaves of groups. But it was originally developed in this book by Giraud, and I don't know a better reference. So if anyone else here does, you should feel free to put it in the chat. Or just unmute yourself and let me know. It's actually a surprisingly useful thing. So for example, Wan Lin, who's here today, and I are currently writing a paper, which will hopefully be done very soon, where we use some kind of long exact sequence in non-abelian group cohomology. But it's also a little bit complicated. Okay, so I'm not going to give you all the details of what how you make a sort of partial long exact sequence from a short exact sequence, what I will do is I'll remark it's a little bit subtle. So what you get is a long exact sequence of sets. Which terminates at what we're interested in, H2GM, and that itself is even special. So you usually don't even get a boundary map from the H1 of PGLN, or H1 of this thing on the right to H2 of the thing on the left. You need more than this, that this is abelian. You need it that it's actually in the center, which is true in our situation. Okay, so let's try to make this explicit. So let's make delta explicit in terms of check cohomology. Okay, and maybe let me remind you, that's in fact the only way we have to make sense of this set here, right? We actually define this set to be the set of Etale locally trivial PGLN torsors, and we said that, well, that has a sort of description in terms of check H1. Like the boundary map in check cohomology doesn't make sense usually for a non-abelian group, but in very low degree, like degree 1, it does. Okay, so can anyone tell me how you would try to do that? So how would you make this boundary map explicit in terms of check cohomology? So basically what I'm asking you to do is implement the snake lemma, right? That's where the boundary map in a long exact sequence comes from. So can anyone tell me? So let's start with, let's start with T, an element of H1 X Etale PGLN. So T is a PGLN torsor, and it's split by some cover U to X, right? And that's because it's a locally trivial PGLN torsor. All right, so what now?
On the intersections, it has to be given by isomorphisms of projective space, which are like PGLs.
Yeah. So okay. So there's an implicit lemma here that Ben is using. Well, so first of all, there's no projective space here, right? So we'll relate it to projective space in a minute. But yeah. So what you're right is that on the intersections, so on U cross U over X, the descent data is given by some section gamma in U cross U over X with some section to the sheaf PGLN on this. Well, why is that? So this is something we've discussed a couple times now. It's just that what is descent data? It's an isomorphism on this double intersection. And automorphisms of PGLN as a PGLN torsor are the same as sections to PGLN. Okay, so what now? So this descent data satisfies the cocycle condition. That'll be key in a little bit. I mean, all descent data satisfies the cocycle condition, but I want to make it explicit. Okay, so what now? So now we have an element of the check complex. So how do we apply the boundary map to it? Can anyone tell me? So how do you do a boundary map? So you when you make the snake lemma, you do some little zigzag, right? So what's the next step? Okay, well, what we do is that we maybe have to refine U. We can lift this descent data to a section, and I'm just going to use the same U, of GLN. Can anyone tell me why this is possible?
because it's surjective, right?
Yeah, so this is a surjection of schemes. So okay, there's a little subtlety in why you can refine U rather than U cross U. And in fact, if you want to work in complete generality, you should refine U cross U, but I'm going to ignore that issue for now. Okay, so we've now lifted this descent data to a section of GLN. So how are we going to make an element of H2 of GM from that? So H2 of GM is represented by a section to GM over U cross U cross U, right?
So you want descent data for GLN, but you don't quite have it because it might not satisfy this co-cycle condition on the nose. It might differ by a co-cycle of constant of functions, right? Like PGLs.
That's exactly right.
GMs.
That's exactly right. So we started with something which satisfies the co-cycle condition, and we just lifted it in an arbitrary way. So there's no reason for it to satisfy the co-cycle condition. So let's write out what that says. So let's take the pullbacks. So pi 1, 2 pullback of S, pi 2, 3 pullback of S, and we can multiply them. So pi 1, 2, pi 2, 3. So normally we'd want that to equal pi 1, 3. So we can measure this, but it's failure to be that by taking pi 1, 3s inverse. Okay? And this, the claim is that this is a section to U cross U cross U with coefficients in GM. Well, why is that? A priori, it's just a section to GLN, but we know that this is 1 when you map to PGLN. So that means that it has to come from GM. Okay, and this is a 2 cocycle, this is the claim at least, representing an element of H2 x Etale GM. Okay, and there's a couple things to check there. The main one is that you have to check it actually satisfies the cocycle, that D of it is 0. And that's something that I'll leave you as an exercise. All right, are there any questions about this? Okay, so this is the map explicitly. So what I would say is what we've done actually is we've proven the following kind of slogan, which is that delta of this torsor T is the obstruction to lifting T to a GLN torsor. Okay, and that's sort of what you would expect. Like the image of something under a boundary map should be the obstruction to lift to it coming from the previous thing, right? So what we're saying is this class, this is called the Brauer class of T. Is the obstruction to doing that. Okay, so let's talk about this. So okay, so far we now have defined this map. We still don't know that its image is a group. So its image right now we've just mapped from some set to a group, and there's no reason why the image of such a map should be a group. And we also don't know yet that it actually lies inside of this cohomological Brauer group because we don't know that the image is torsion. All right. So in order to prove that, we're going to have to do some geometry. So what I want to discuss now is kind of geometric interpretations of Brauer classes. So of both PGLN torsors and Brauer classes. Okay, so before I do that, are there any questions?
So just to clarify, so by delta of T obstruction, you mean that may be a non-trivial.
Yeah, so I mean, that being non-zero is the obstruction to lifting your PGLN torsor to a GLN torsor. Does that answer your question, Arvin?
Yeah, thanks.
Yeah. Yeah, so in particular, if it is 0, you can lift. Great. Yeah, and this is, by the way, this is sort of a general principle. So sometimes, you know, people will do similar things with, instead of instead of like GLN mapping to PGLN, you might do like O of a quadratic form Q mapping to P O of Q. Yeah, so this is sort of a general principle that sometimes you can make kind of abelian cohomology classes as obstructions to lifting non-abelian torsors from one group to another. Great. Okay. So let's talk about this. So here's first of all a general principle, and we've talked about this a little bit, but I want to kind of remind you. So suppose T is an object just in sheaves of sets on X Etale, and again this will work on any site, and G is the sheaf, which is aught of T. So sections of this are over an open are you pull back T to the open and then you compute aught of it. So for example, T can be a scheme, and in all of our examples, we'll just think that T is a scheme. All right. So the general principle is that there's a natural bijection between locally split G torsors and forms of T. So we've talked about this before. So for example, when we talked about GLN torsors being the same as vector bundles, this is an example of this. So in this case, we would take T to be the trivial vector bundle, and G is GLN. Okay, so what do I mean by form? So by a form of T, I mean a sheaf on X locally isomorphic to T. So for example, a vector bundle is locally isomorphic to a trivial vector bundle. So this correspondence between G torsors and forms, when you apply it to GLN and the trivial vector bundle, says that GLN torsors are the same as vector bundles. All right, so can anyone tell me how to make this bijection? So how do you go from right to left, for example? So how do you go from a form of T to a G torsor?
Take the sheaf of automorphisms.
Or maybe the sheaf of isomorphisms?
Sorry, that's what I meant, yeah.
Yeah, so starting with the form F, we can take the isom sheaf from F to T. This is if you want, I guess I've been vague about whether I want right or left torsors, so this is if you want a right torsor, otherwise you would do isom TF. Okay, why is this locally split? Well, because F is locally trivial, it's locally isomorphic to T, so if you base change to some cover where F is actually trivial, then this torsor will be split. All right, what about how do you go from a torsor? Unfortunately, I've used T for my object. What's a good, let me call it tau as a torsor. So how do you go from a torsor to a form? Can anyone tell me?
I think I've heard you say this before. You take the product of tau with the trivial torsor.
Yeah, so you take tau times T, the thing we're taking the forms of, and then you take the diagonal quotient by G. So this is the sheaf quotient. But in good cases, this quotient will actually be representable by a scheme, and that usually won't be so hard to see because G here acts simply transitively on this torsor. So basically all this quotient is doing is getting rid of this tau part and making the fibers isomorphic to T instead. Okay, so here's some examples. I've already discussed this a couple times. So GLN torsors are the same as vector bundles. Okay, maybe it's worth mentioning, there's a reason I'm writing these arrows going both ways rather than saying it's an equivalence of categories. And it's because it's not an equivalence of categories. So there are maps between vector bundles which don't come from maps of torsors. For example, any map which is not an isomorphism will not come from a map of torsors. So what this really means is that what I mean by this double arrow, if you would like a rigorous statement, is that there's a bijection between the two sets of GLN torsors up to isomorphism and vector bundles up to isomorphism. Okay. All right. So now let's get to talking about the situation with PGLN. So let's do PGLN. So now let's talk about G is PGLN. So what we're doing is we're looking for objects with automorphism group PGLN. So what are some objects with automorphism group? Isomorphic as a sheaf to PGLN. So can anyone give me some examples? So what's your favorite thing with automorphism group PGLN? So this I know you know. In fact, someone said it a few minutes ago.
Projective n space.
Yeah, that's, well, maybe projective n-1 space.
N-1, yeah.
Yeah. So example, so aught over x of p n-1 x is PGLN. Okay, maybe it's worth remarking, so you've probably all done this over an algebraic closed field. It's true over a general base, and it's not totally trivial. So when I write x, I actually mean exercise, so you should prove this. And it's not trivial, so I think you'll probably need to use something like the theorem on formal functions at some point, or formal gaga, or whatever form of that you would like to use. So what this tells us is that there's a natural bijection between PGLN torsors up to isomorphism and forms of Pn. Okay, and these have a name. These are called Severi-Brauer schemes, or Severi-Brauer X schemes. And if X is a point, if X is spec K, you usually say they're Severi-Brauer varieties.
I think you mean forms of Pn-1.
Oh yeah, sorry about that. Great. Can anyone give me another example of an object with automorphism group PGLN?
CSAs,
I'm sorry?
central simple algebras.
Yeah, so a central simple algebra in general won't quite have automorphism group Pn. Yeah, but what is true is that a matrix algebra will, right? So example, the algebra of n by n matrices over a ring. So out of this is PGLN. And this is called the Skolem-Noether theorem. Or maybe Noether, I don't know why I put Skolem first, but I think that's how it's usually written. But maybe I'll put it in alphabetical order. Noether-Skolem theorem. So what that tells us is that there's a bijection between PGLN torsors and forms of mat n by n. So here, if you'd like, you can think of this as end of the trivial vector bundle. Okay, and forms of this algebra have a name. They're called Azumaya algebras. Okay, and over a field, those are central simple algebras. So there's a fact, which we'll maybe even see in a little bit, depending on how much time we have, that's just things over a field are always matrix algebras over a division algebra. All right. Great. So let me remark, I mean, okay, in principle, we've given a recipe. We can go from a form of Pn to a PGLN torsor and then from that PGLN torsor to an Azumaya algebra. But it's not actually so obvious how to go directly from the Severi-Brauer to the Azumaya algebra and back. And so I want to discuss a way to do that, and it's a way that I really like to think about Brauer classes and forms of PGLN and so on and so forth. But before I do that, are there any questions?
Is it frozen for anyone else?
Can you when you say it, do you mean me?
It doesn't seem frozen. Can you, yeah, he can scroll up and down on my screen.
Arvin, can you see it now?
Oh, now it's good. Sorry, I think it was my fault.
Okay, cool. All right, so are there any other questions about these sorts of, so the key takeaway here is that, okay, the Brauer, well, right now we just know it's a set, the Brauer group, which will prove it as a group in a little bit, objects of it have representatives which are very concrete. So namely forms of Pn minus one, so you can think those are like Etale locally trivial Pn minus one bundles, or forms of a matrix algebra. So those are like quasi-coherent sheaves of algebras, or sorry, coherent sheaves of algebras, which Etale locally look like endomorphisms of the trivial bundle. Okay, are there any questions about those? All right, so this is how people usually think about Brauer groups. They think about it as in terms of one of these two objects, so Azumaya algebras or PGLN torsors. I want to give you a third way, which I think is really cool, and I'm going to kind of sketch how to prove things in terms of these objects called twisted sheaves. Okay, so we've actually already basically said what a twisted sheaf is. So let me scroll up over here and show you what we did when we defined this boundary map. So when we defined this boundary map, what we did is we said we had some descent data for PGLN. So that was on double intersections, some elements of PGLN, and we lifted those to elements of GLN. Okay, so here's another way of interpreting what we did. So definition. So I'm going to let alpha, so let u to x be an Etale cover, and alpha an element of the check complex on the triple intersection of u over x with GM coefficients. Oh boy, there's someone doing leaf blowing literally right outside my window. Is that, can you guys hear that? Is it making what I'm saying incomprehensible?
It's fine, I think.
Okay, good. All right, so suppose I have an Etale cover and some alpha in here, and suppose alpha represents, so suppose it's an honest two cocycles. So suppose it represents some class alpha in H2 X Etale GM. So I want to tell you what an alpha twisted sheaf is. So an alpha twisted sheaf and note here, I'm honestly twisting by the cocycle, not by the Brauer class, is a sheaf on U. So by a sheaf, I mean a quasi-coherent sheaf on U. An isomorphism, it's called phi, from, let's call it a sheaf, maybe a sheaf F on U. So an isomorphism between the two pullbacks of F to U cross U. So this looks like descent data, except we don't want it to be descent data. What we want is that it satisfies the cocycle condition up to alpha. So what does that mean? It means that pi 2, 3 pullback of phi composed with pi 1, 2 pullback of phi is alpha times pi 1, 3 pullback of phi. Okay, so if alpha was just the constant function 1, this would be an honest sheaf. It would be descent data for a quasi-coherent sheaf, but alpha is not necessarily 1. So here we're twisting what it means to be a sheaf. Are there any questions about this definition? No? Good. Okay, can anyone tell me how one of these might show up naturally? We've actually already seen some.
Is this like a PGL torser?
Yeah, so this is exactly what we did when we were defining this boundary map. So what do? We start with a PGLN torser, lift to a GLN torser. So maybe we can't do that on U, but you can actually always lift to because our torser is split on U, you can always lift to a quasi-coherent sheaf on U. And then we got some isomorphisms between those sheaves, these GLN torsers on the double overlaps. Okay, and those isomorphisms failed to satisfy the cocycle condition. And in general, the 2 cocycle that measures that failure was exactly a Brauer class. So when we defined this boundary map delta, our intermediate step was precisely an alpha twisted sheaf. All right. So we now know at least what the object of the category of alpha twisted sheaves are. So I'm going to define a category. So this is called QCO X alpha. And the objects are alpha twisted sheaves. And the morphisms are the obvious thing. So the morphisms are morphisms of sheaves on U commuting with this pseudo descent data phi. Okay, so this is some cool category. Just as an example, if you take the constant cocycle 1, so there's implicitly in this definition is a cover U, but I'm considering that as part of the data of alpha. So if you take QCO X comma 1, so where with any cover, this is going to be canonically isomorphic to QCO X. Can anyone tell me why? So this is the name of this theorem is it has a very famous name. We talked about it a couple weeks ago.
Descent?
Yeah. So this is Etale descent. Great. Okay. So this is a category. It's a pretty cool category. Let me tell you some facts about it. And I'm not going to prove all of them, but I'll prove a couple. So here's a proposition. So suppose that alpha and alpha prime are 2 cocycles for GM. So the kind of things that lets us define let us define a twisted sheaf. So 1, alpha being a Brauer class, so meaning the cocycle represented by alpha, suppose it lives in Brauer of X, meaning it's in the image of this boundary map from PGLN. So this is the same as there existing an alpha twisted sheaf. And in fact, we proved that already, right? What being in the Brauer means you're in the image of delta, but part of our construction of delta was to construct a alpha twisted sheaf from a PGLN torser. All right. 2. So this category, QCO X alpha, is an abelian category. That's actually easy. And then the hard part is that it has enough injectives. And this is if X is nice. And let me not dwell on what that means. All right. I'm sorry?
You said we constructed a twisted sheaf, right? And that's the one that we get by quotienting out, like taking the product and quotienting out.
No. So that was the torser associated to that was the twisted form associated to a torser. So when we constructed a twisted sheaf, up here, when we started with a torsor, we got some cocycle with values in PGLN, and we lifted it to a cocycle with values in GLN.
Okay, cool.
Right, and then that cocycle didn't quite satisfy the cocycle condition, and that's exactly what it means to be a twisted sheaf.
Cool, thanks.
Yeah, this is kind of a funky way of thinking about things, but I really like it because you can really think of twisted sheaves as just being like almost like sheaves. Like they're very familiar objects. Okay, so now there's a tensor functor from QCO X alpha times QCO X alpha prime. And where does it land? It lands in QCO X alpha times alpha prime. Okay, there's a little subtlety here. If alpha and alpha prime are defined on different covers, you have to pass to a common refinement and work there. But I'll let you think about this. There's also a Hom functor from QCO X alpha times QCO X alpha prime to QCO X alpha prime minus alpha. Okay, and how do you make this functor? You literally just tensor your sheaves on U together, or Hom your sheaves together, and use the induced pseudo descent data. Okay, similarly, there's functors sim n, for example, and wedge n, which go from QCO X alpha to QCO X alpha prime, X n alpha. Sorry, I lied, by the way. I shouldn't, up here I shouldn't have said twisted sheaf. I should have said twisted vector bundle. Very sorry about that. That just means the sheaf on U is a vector bundle. Okay, and finally, and I already said this, QCO X1 is canonically equivalent to QCO X. All right. So let's talk through some of these things. I'm especially not gonna give a proof of two. It's not hard, it's just involved. So one we already talked about. So suppose alpha is in Brauer of X. That means that there's a PGLN torsor whose boundary is alpha. Okay, and then we already constructed an alpha twisted vector bundle out of it. That was precisely our construction of delta. Can anyone tell me how to go the other way? So suppose I'm given an alpha twisted vector bundle. How do I get a Brauer class? Anyone? Well, one thing you could do is you could try to construct a twisted form of Pn. So how would you do that from a twisted vector bundle?
You take proj?
Yeah, you can take you can just projectivize it. So you have a vector bundle on U. Its projectivization is a Pn bundle on U, and now your descent data, your pseudo descent data, which used to not be descent data, is actually descent data, because when you projectivize, you mod out by scalars, and the failure to be descent data was exactly scalars. All right. So this tensor and Hom, you just have to work out what happens to alpha and alpha prime when you tensor your twisted sheaves together, or Hom them together. Same with sim n and wedge n. So in fact, everything except for 2 is more or less directly from the definition. So proof is to actually, let me just leave as an exercise, try to prove 3 and 4. Okay, so there's an immediate corollary, which is that Brauer of X is a group. Can anyone give me the proof? Oh, so Arvind asks, can you give an explicit example of an alpha? Is it right to think that it's something that becomes trivial after an Etale base change? So alpha is it's not usually going to be trivial. Alpha is going to be like an invertible function on U cross U cross U. But what is true is that locally it'll be the boundary of something, right? So that's that's sort of true of cohomology in general. If you're on a nice enough scheme, so for example, a quasi-projective variety, any class with cohomology in any abelian sheaf in degree bigger than 1 is locally at the boundary of something. All right. So, okay, can anyone prove to me using this proposition that the Brauer group is a group? So remember, all we defined it as was some set. It was the image of some boundary map from a set.
Let's see, let's take a group operation to be tensor product.
Yeah, so what does it mean? So suppose we have alpha and alpha prime. So then, so those are, we can think of those as, so we can let E be an alpha twisted vector bundle.
Mm-hmm.
So that exists by this 1. We can let E prime be an alpha prime twisted vector bundle. And we want to show that alpha times alpha prime is a Brauer class, meaning there exists an alpha alpha prime twisted vector bundle. And well, as Sasha said, E tensor E prime is an alpha alpha prime twisted vector bundle. And having a twisted vector bundle, we said, was the same as being a Brauer class. All right, so what about inversion? So how do we show that the inverse of a Brauer class is a Brauer class? And Arvin, don't worry. I see Arvin in the chat is asking about explicit examples. I'll discuss a couple explicit examples of these objects in a minute. All right, so how do we do inversion? My hint is that there's a minus sign appearing here.
Mm-hmm.
So in other words, we want, so this gives us the product. Okay, now we want, suppose alpha is a Brauer class, and here E is an alpha twisted vector bundle. We want an alpha inverse twisted vector bundle. Okay, and can anyone make one?
The dual effect?
Yeah.
bundle? Yeah.
Okay, and that's an alpha inverse twisted vector bundle.
Mm-hmm.
Sorry, I wrote this minus. I wrote it additively here. Let me write it multiplicatively, which I've been doing everywhere else. All right. So we've now proven the Brauer group is a group. Great. I just want to prove a couple more basic facts about the Brauer group, and then I'll give some examples. So here's the sort of proposition. So suppose alpha is a 2 cocycle for GM. Then alpha is trivial if and only if there exists an alpha twisted line bundle. Can anyone prove this for me? So let's do the first direction. So suppose E is an alpha twisted line bundle. How do we show that alpha is trivial? Well, maybe the easier direction is this way. So suppose alpha is trivial. Can anyone make for me an alpha twisted line bundle?
What would the OX be a line
Yeah.
bundle?
So OX is. So there's an implicit lemma here, which is that if alpha is isomorphic to alpha prime, so meaning the Brauer classes are the same, then QCO X alpha is equivalent to QCO X alpha prime. And I've carefully wrote this is equivalent without an arrow here because it's actually not a canonical equivalence. But so you should prove this lemma. It's easy, in fact, but it's an exercise worth doing. Okay, but once you have this, well, if alpha is trivial, then that means that the class of alpha is the same as the class of 1, which means that this category is abstractly equivalent to the category of quasi-cogent sheaves on X, and then OX is a honest line bundle. All right. What about the other direction? So suppose I have an alpha twisted line bundle. So let me remind you, how do you write down a line bundle? Well, you take a cover, you take the trivial bundle on each cover, and then on double intersections, you have gluing data, which is a section of GM on the double intersections. So how would you use such a thing to prove that that alpha is a trivial Brauer class, so trivial on H2 of GM?
Well, so you have like a for n equals 1 in the exact sequence, it's just like GM goes to trivial goes to GM. So you would expect that the boundary map of a line bundle is always 0 in the Brauer. Or,
Yeah,
sorry,
that's
always
actually
the
totally,
boundary.
that's a perfectly good proof. Let me be a little bit more explicit about what you just said. So here are the descent data for L. All that means is the gluing data I just described is the same as a global section to GM on U cross U for some U. Okay, and then so let me call it beta. And then the claim is that the check differential applied to beta is just alpha. Okay, and that's what it means for alpha to be 0 in H2 of GM. Okay, and finally, let me prove a cool corollary. So suppose E is an alpha twisted vector bundle. Of rank n. Then the class of alpha in H2 X Etale GM is n torsion. So we just proved this when n is 1. So can anyone tell me how to deduce the general statement? So how do you make a line bundle out of a vector bundle?
Determinant or something?
Yeah, take the top wedge power. So wedge n of E, which we said is something we could do to twisted sheaves, is n. And we said that this, if we scroll up to this proposition from before, we said that wedge n multiplies the Brauer class by n, or takes it to the nth power in multiplicative notation. So what that tells us is that this is a n alpha, or maybe I'll write it as in multiplicative notation, alpha to the n twisted line bundle. Okay, and by the previous proposition, this implies that alpha to the n, which is alpha to the n, is trivial. Cool. Okay, so we've now proved that the Brauer group is a group, and we've moreover proven its torsion. So corollary, Brauer of X is a subset of Brauer prime of X, which remember was the torsion in the Etale cohomology of X with coefficients in GM. Great. All right, let me give you some examples because this has gotten very abstract. So can anyone give me, let's just talk about some examples of Brauer classes. So can anyone give me some examples of let's say, Azumaya algebras or twisted forms of Pn or whatever you'd like? So what's your favorite twisted form of P1?
Brauer Severi varieties?
Which one? You have to give me an
Oh, okay.
No.
Something like x squared plus y squared plus c squared. No, actually that has a solution.
Well, over which field?
Um,
And what does it equal?
R, I guess, would be good.
Yeah, so if we set x squared plus y squared plus c squared equals 0 over the real numbers, so this is a conic with no rational points. So a smooth conic over no rational points. And we know this is, what's it called? It's a stereographic projection, I think it's called. That if you have a conic with a rational point, a smooth projective conic with a rational point, it's isomorphic to P1. So this is something that becomes isomorphic to P1 when you base change to C, where you have a rational point. So this, so let's call this X. So XC we know is isomorphic to P1. And this implies that X is a twisted form of P1R. Okay, and in fact, the class of X, so if you take delta of this X, it generates the Brauer group of R, which is Z mod 2. Can anyone tell me what is the generator of this Brauer group if we want an Azumaya algebra, or also known as the central simple algebra, since we're for a field, rather than a Severi-Brauer?
Is it the quaternions?
Yeah, the Hamilton quaternions. Are they're a division algebra, in fact. Hence, or central division algebra, hence an Azumaya algebra. Representing the same element.
Is there a map directly from the Azumaya algebras to the twisted forms of Pn?
That's a good question. Yeah, so let me say how I think about it. So I think of both of them coming from twisted sheaves. So let's actually write out the diagram. So given an alpha twisted sheaf, E, one thing you can do is you can take the projectivization of it. So this gives you a Severi-Brauer. And there's a little subtlety here, so let me say what's happening. So an alpha twisted sheaf is a vector bundle with twisted descent data. When you projectivize, that twisted descent data becomes honest descent data because it was twisted by a scalar, and projectivization kills scalars. All right, but there's a little bit of subtlety, which is that descent data is not effective for schemes, right? So to actually say there's an honest variety rather than just like a sheaf representing this descent, you need a little bit of extra argument, and the argument is that projective space is anti-canonically polarized. So I think I remarked on this, but we didn't prove it, which is that if you have descent data for a polarized variety, meaning a variety plus an ample line model on it, then it's effective. And any descent data on projective space is automatically polarized because there's kind of a canonical polarization, namely the dual of the canonical sheaf. All right, now let's also say how to get an Azumaya algebra. Well, we just take end E, and this is an Azumaya algebra. So taking end kills the twisting cocycle, so we get honest descent data. So we get an honest sheaf of algebras. And why is it locally isomorphic to a matrix algebra? Well, it's because if you pass to a cover of U where E itself is trivialized, then it's a matrix algebra. So that's how I think about it. So I think of the map between these two things as kind of passing through twisted sheaves. Does that answer your question, Ben?
Yeah, I'm just wondering if you can show how the quaternions are end of this scheme over R in some sense.
Yeah, I mean they're not end of the scheme of R. So
the twisted sheaf associated to this.
Yeah, so you could do that directly. I don't think it would actually be super hard. But I'm not going to try to do it right now because I'll definitely screw up. Maybe I will remark. So there is a direct way to go from Azumaya algebras to Severi-Brauers. So these are moduli. The Severi-Brauer associated to an Azumaya is the moduli of certain ideals in the Azumaya. But I'd have to think a little bit about what the right formulation is. I don't remember off the top of my head. I don't know a slick way of going the other way from the Severi-Brauer to the Azumaya. Are there any questions about that? Yeah, that's a great question. All right, so I did want to give a couple more examples of Brauer classes because this is like a beautiful thing. So does anyone know any other examples? I saw Ben briefly unmute. Did you have an idea?
Well, I was gonna say like all the ones in class field theory, but then I realized I couldn't actually write any of them down.
That's all right. Yeah. So it's pretty hard to write them down in general. Let me kind of actually I wanted to give kind of class field theory as an example. So the Brauer group of QP. Does anyone know what it is? Or QP is the p-adic field?
Q mod Z.
Yeah. So it's Q mod Z. And in principle, you can write down honest representatives of all these classes. So it's done, I think, in Castle's Froelich algebraic number theory book, for example. I'm not going to try to do it, but maybe the remark is that over a field, any two-torsion Brauer class is represented by a quaternion algebra. So what I mean by that is you take the formula for the Hamilton quaternions, which says that some things square to -1, and you change those -1s to some other numbers. So in general, for the unique two-torsion element of this Q mod Z, so that's like 1/2, the cocycle of the coset of Z corresponding to 1/2. That's represented by a very explicit quaternion algebra, which looks very much like the Hamilton quaternions. All right. So we already said what the Brauer group of R looks like. We can also say what the Brauer group of Q looks like. So there's a map from the Brauer group of Q. Well, given an Azumaya algebra or a Severi-Brauer, for example, over Q, you can restrict it, you can pull it back to QP, right? Or to R. So there's a map to the direct sum over all the places of Q, including infinity, so including R, to the Brauer group of the completion of Q at that place. So for all finite places, we just learned this is Q mod Z. For R, it's Z mod 2. The map is to the direct sum, meaning that for almost all places, the Brauer class will split. And that's actually a really fun exercise, which I'll say a word about in a second. All right, and now you can add these things together, and the co-kernel, it turns out, is this map where you add these elements of Q mod Z or Z mod 2, which you can think of as the half integers mod Z, to this maps to Q mod Z just by summing, and this map is surjective. Okay, so there's a fairly explicit description of the Brauer group of Q and in fact of any number field. Are there any questions about this? I mean, this is highly non-trivial, this stuff. So maybe a fun exercise is to use the Severi-Brauer interpretation to show that if alpha is in Brauer of Q, alpha restricted to Q nu, so the completion of Q is 0 for almost all nu. Okay, and this is a really fun exercise. You should do it. It's great. All right. Are there any questions about that before I move on? I guess I have 10 minutes left.
Where exactly do you need to use class field theory here? I mean, I guess you need it for the injectivity of the left arrow?
This is part of the statement of class field theory, I would say.
Well,
Yeah.
Okay.
Yeah, I mean, it's like it shows up when you do the proof.
Okay, fair enough.
You the Brauer group of a number field.
Sure, okay.
Yeah. Yeah, it's not. It doesn't. I mean, it doesn't follow from class field theory, except insofar as it's like literally part of the statements. It's like if you go through Castle's Froelich, like a huge amount of it is working out Brauer groups. Yeah, one way to say it is that class field theory is so you can think of this isomorphism as being a certain element in H2 of a local field. And the reciprocity map is cupping with that element. So like this isomorphism literally is the key.
Okay, sure. If you do the cohomological approach. Okay.
Yeah.
Cool.
All right. Cool. Any other questions? Anyone want to see more examples?
Can you is it possible to describe the multiplication in the group in terms of, like twisted forms of projective space?
Yeah, so let's do that. So we can do Azumaya algebras first. Maybe that's easier. So suppose so let's interpret multiplication. So suppose A1 and A2 are Azumaya algebras. Representing some classes alpha 1 and alpha 2. Then alpha 1 tensor alpha 2 is an Azumaya algebra representing alpha 1 times alpha 2. All right, so it's not totally obvious that this is an Azumaya algebra. Can anyone tell me why it is? So remember, Azumaya algebra was a twisted form of a matrix algebra.
Yes, because if you tensor two matrix algebras, then you get a matrix algebra.
Yeah, exactly. So being in Azumaya algebra is a local property, so you can just pass to a cover where your thing is literally a matrix algebra, and then this is just a fact about matrix algebras. All right, so let me think. So how do we? Yeah, so it's not totally obvious to me how to do this in terms of Severi-Brauers. So the easiest way to say it is, now suppose that P1, which is the projectivization of some twisted sheaf E, and P2 is the projectivization of some twisted vector bundle E prime, are Severi-Brauers, representing alpha 1 and alpha 2. So here, this is alpha 1 twisted vector bundle, and this is alpha 2 twisted vector bundle. Then I guess the projectivization of their tensor product represents alpha 1, alpha 2. Let's think if we can find it. I guess what you can do if you want to do this geometrically, and maybe I'll just say it verbally, because since writing it out carefully would be a little bit complicated. Severi-Brauers come with a natural embedding in projective space, given by the anti-canonical line bundle. And I think what you can do is you can take the Segre embedding of the product and then take its span. And I think that will, is that quite right? That's not quite right. So what you need to do is take some intersection of quadrics cut out by that contains in it. But I would need to think a little bit to get it exactly right. So maybe let me not try to do it right now. Yeah, so I think there is a geometric way you could write down this space in terms of the anti-canonical embeddings of the Severi-Brauers, but I don't want to attempt it in the next 6 minutes. Is that okay, Arvin?
Yeah, I'm happy. Thanks.
Yeah. Okay. Yeah. So I think this is maybe the easiest way to think about it. One question, by the way, and this is something Kalara I know has been thinking about recently, is it's not so easy to write down equations for Severi-Brauers. So it's kind of closely related to writing down equations for the anti-canonical embeddings of projective space, and that's just not a totally trivial thing to do. So yeah, I think we can write down equations for Severi-Brauer curves, so conics. That's pretty easy. But I think above that, even Severi-Brauer surfaces, like I think Kalar managed to write down like birational models in some generality, but I don't think we know how to do much with threefolds. Yeah, so this is a really interesting area to try to make explicit. All right, any other questions? All right, I only have 5. Oh, Sasha, did you have a question?
Yeah, one quick question. So two torsion elements in the Brauer group give you, I guess, quaternion algebras. Do you know much about kind of the higher torsion?
That's true in the field. It's not true in general.
Oh, well, yeah, over a field. But sure, over a field, so 2 torsion gives you quaternion algebras, but do we know about higher torsion in general? With those
Yeah, so it's really, yeah, so there's a kind of big open question called, which is broadly speaking called the period index question. Which is, and let me give you a loose formulation. So given alpha in the Brauer group of X, and people mostly think about this when X is a spec of a field, can you find, so maybe what is the minimum rank or GCD of the ranks, etc., of an alpha twisted vector bundle? Or for example, what is the minimum rank of a Azumaya algebra representing alpha? So that's the square of the minimum rank of a alpha twisted vector bundle. And it's a really hard question. So for 2 torsion over a field, we can do it. It's easy. It's always, you can always find something of size 2. But in general, this is a really hard question, and we know of examples where in general, it's if you have a alpha twisted vector bundle of rank n, alpha is n torsion, but the converse is definitely not true. Yeah, so again, asking for explicit representatives of these things, meaning especially like kind of small representatives, is like a really hard open question. Does that answer your question, Sasha?
Yeah.
Cool. All right. I think we're basically out of time, unfortunately. So maybe let me kind of briefly say what we're going to do next time. So next time is we'll use the theory we've developed today to understand HI of a field with coefficients in GM. So in particular, the main theorem we're going to try to prove is suppose so K of C is the function field of a curve over an algebraically closed field, then H2 of K of C with coefficients in GM, so in particular the Brauer group, will be 0. And then we're also going to show, so suppose Kx bar is a strictly Henselian DVR. So if we have time, we'll show that H2 of Kx bar also with coefficients in GM is 0. Okay, and this will be the key ingredient to finish computing the Etale homology of curves, which we'll hopefully do next time. All right, so we're out of time, so let me stop recording. I'll stick around for a few minutes if anyone has any questions.